Hey guys, this is AC Service Tech, and today what we're looking at is the HVACR Basic Refrigeration Cycle Training. In this example, we're using a walk-in cooler box to go over the refrigeration cycle. So what you have is low pressure, low temperature vapor heading into the compressor. The compressor is located in the outdoor unit, which is the condensing unit, and you have low pressure, low temperature vapor going through the vapor service valve into the compressor, which you should have vapor only heading into that compressor, and then you have high pressure, high temperature discharge vapor gas coming out of the compressor. So that's high pressure, high temperature vapor, and what happens is that compressor takes low pressure and it compresses it, turns it to high pressure, and since it's high pressure, it's therefore high temperature. So temperature follows pressure. Where it comes out of the compressor, that's called the discharge line. So it rides in the discharge line until it goes into the condenser coil, where it's rejecting heat to the outside air. It starts rejecting enough heat until it ends up turning into the saturated state. That's where liquid and vapor both exist at the same time. So that's that dark red and the light red colors were in the condenser coil there. So that's the saturated state. That's where most of the heat is being rejected from in that saturated state. There is no temperature change once it hits that saturated state. So then it continues to reject heat, reject heat, reject heat until it turns into a complete liquid. Then the liquid refrigerant lowers in temperature as it rejects heat and turns into a subcooled liquid. The subcooled liquid is the temperature difference between where it comes out of the saturated state as a complete liquid until where it comes into the liquid receiver. Subcooling is the temperature decrease in liquid form. The liquid receiver is a storage vessel for the subcooled liquid. So the amount of liquid that will be in that liquid receiver has a direct correlation to how cold that walk-in box is. So if it's very cold in that walk-in box, then the system doesn't need as much liquid refrigerant, so therefore it's stored in the receiver. When you just start a walk-in box up for the first time, that liquid receiver should be drained just about all the way down to the bottom there. And you should have a solid column of liquid heading through that liquid sight glass. That's kind of verifying that you still have enough subcooled liquid to head to the TXV, but you don't want to add extra refrigerant to the system that will be stored in the liquid receiver. So the subcooled liquid then ends up getting sucked up the tube through the liquid service valve on the top of the receiver, and then it goes through the filter dryer, and the filter dryer's job is to store any water vapor and any contaminants, and it stores the water vapor so that does not interact with the refrigerant oil. If water vapor and refrigerant oil mix, it turns into alcohol and acids. So then the liquid refrigerant, subcooled liquid refrigerant, heads through the filter dryer, heads through the solenoid valve. On the system that you're working on, it may or may not have a solenoid valve. If it doesn't have a solenoid valve and it doesn't have a pressure control, then that system is just turned on and off by a mechanical thermostat or an electronic thermostat. But in this case, we're going to be showing a liquid solenoid valve that will be used as a pump down feature on a system with a low pressure control. So the subcooled liquid refrigerant heads through the liquid solenoid valve, and then it goes through the liquid sight glass. The liquid sight glass could be in the outdoor unit, and more preferably it's right in front of the thermostatic expansion valve. But some outdoor units come with the liquid sight glass already there. Once again, it's best to actually have that closer towards the thermostatic expansion valve, right in front of it. So as the subcooled liquid heads through the liquid sight glass, if you have a solid column of liquid, which means you have subcooled liquid, that liquid sight glass will be clear unless there's some type of obstruction in the way, like a clogged filter dryer. So then it heads through the liquid sight glass as a subcooled liquid, and then it heads over into the thermostatic expansion valve as a high pressure, high temperature, subcooled liquid refrigerant. Then it ends up going through the thermostatic expansion valve, which is a metering device, and it lowers in pressure and lowers in temperature and turns into a low pressure, low temperature liquid refrigerant. It's actually about 80% liquid, 20% flash gas, but in this case we're just going to show it as a low pressure, low temperature liquid refrigerant. As it heads into the evaporator coil, it ends up absorbing heat from inside the walk-in box. As it absorbs heat from the walk-in box, the liquid refrigerant increases in temperature and it turns into that saturated state where liquid and vapor both exist at the same time. Once the refrigerant's in the saturated state, that's where most of the heat is being absorbed at, in that saturated state. Then once the refrigerant absorbs enough heat while maintaining that same temperature, it then turns into a complete vapor. Once the refrigerant's a complete vapor, then what happens is it ends up increasing in temperature until it comes out of the evaporator coil. So the temperature difference between where it turns into a complete vapor from the saturated state and then where it comes out of the evaporator coil, that's called the superheat. And that's why you have the thermostatic expansion bulb and the external equalization port mounted on the suction line right after the evaporator coil. That thermostatic expansion valve is actually reading the superheat, and it's trying to maintain the superheat. And in a walk-in box, you're looking for about 6 to 8 degrees of superheat once the temperature in the walk-in box is lower. So then the superheated, low pressure, low temperature vapor refrigerant ends up leaving the walk-in box and heading back to the outdoor unit. And once again, you may have a low pressure control mounted on the suction line before it goes to the compressor. Then the low pressure, low temperature vapor refrigerant heads back into the compressor and the cycle starts all over. So that's how it works. You're absorbing heat from inside the walk-in box, you're rejecting it outside, and the liquid receiver is there because of this varying temperature load inside that walk-in box. So you need more refrigerant when the inside of the walk-in box is really, really hot. And you need less refrigerant when the walk-in box is lower in temperature. And therefore, you have the liquid receiver there to store the subcooled liquid refrigerant so that you don't end up having that liquid refrigerant stuck in the condenser coil. If you didn't have a liquid receiver, it would actually be storing that liquid refrigerant in the outdoor condenser coil. And what happens is that would end up limiting the amount of space on that coil for the saturated state. The saturated state is liquid and vapor, both existing at the same time, and like I said before, that is where most of the energy is being rejected out of the refrigerant and into the outside air. So having a large saturated state in the evaporator coil and at the condenser coil is crucial to a refrigeration system working properly. You have to have complete vapor heading into the compressor. You want to make sure that you don't have any saturated refrigerant heading into the compressor or just straight liquid heading into the compressor. It has to have complete vapor only heading into that compressor. Likewise, you need a subcooled liquid heading into the thermostatic expansion valve, and you need enough complete liquid for that thermostatic expansion valve to open pretty wide up if that walk-in box is high in temperature. Say you're just turning it on for the first time. Then you still need subcooled liquid if the temperature in the walk-in box is lower, and that thermostatic expansion valve is able to throttle down the amount of refrigerant heading into the evaporator coil, because it still needs to be superheated before it comes out of that evaporator coil inside the walk-in box. The thermostatic expansion valve is actually adjusting the amount of flow going into the evaporator coil, and therefore the thermostatic expansion valve is maintaining the same superheat regardless of whether the walk-in box is very low in temperature or it's higher in temperature. Maybe you're starting the walk-in box up for the first time and it's warm inside. You want to make sure that you have superheat, and typically you're going to have 6 to 8 degrees of superheat when the walk-in box is lower in temperature. So that TXV is trying to monitor and achieve that superheat at those lower temperatures inside the walk-in box. That's why you don't have a fixed orifice for a metering device in a walk-in box, because that inside of the walk-in box varies in temperature too greatly to be controlled by just a small piston. Because if that walk-in box is cold already, then there's not going to be that much heat to absorb inside the walk-in box. That thermostatic expansion valve is making sure that you have a superheated vapor heading into the compressor. So that's how it works. If you want to learn more about the refrigeration cycle and heat pumps and how other air conditioning systems work, check out the description below for a playlist there. And if you want to see the tools that are used, I also have links to those in the description below. Hope you enjoyed yourself, and we'll see you next time at AC Service Tech channel.